Oh, Michael?
Hello.
Hey,
How are you?
doing good.
Good.
Let me set the cameras. Hey, Khalid.
Hi, doctor. How are you?
Good, thanks.
Excuse me, doctor. I got confused by the due time for the homework of physics of this class.
Yeah.
I remember you said last time that it will be on Thursday, but now if I got confused with it in DTL, it's due now. So
Did we agree on Thursday by any chance? I thought it was the other course we postponed. Did we postpone the homework for this course?
I remember I wrote it from your notes. It's on Thursday.
Yeah, so I thought last Tuesday, I thought the original date was Thursday for this one.
Oh, I see. So it was Thursday. Okay,
Right.
okay. So everyone seems to agree to that. Okay, so I'll change it to Thursday, I guess.
Thank you.
Yeah, no, it seems like it was my fault.
Are we talking about the homework due date?
Yes. When is
Yeah.
this homework due for this class?
Well, I'm trying to look to see what I have.
I guess I'm used to your schedule, so I knew it was due today, but I think it's just because I'm used to, I've had you several times, but
Yeah, sure. Let me see my
Yeah,
notes.
I thought it was due today. I mean, I turned it in today.
Okay, it seems like there was a confusion, so we'll have it for those who did not submit it. Oh yeah, in my notes it's weird. The date is August 25, but then I write Thursday. So that might have been the confusion. So I write Thursday, but the date is there. So that could have led to the confusion. But you guys might have registered it as Thursday, and some must have registered it as the date. Depends on how you register dates. Yeah.
Yeah, it's also the original date for the other class was on Monday, and you changed it to Friday. So
That's correct, yeah. But that should not be, yeah. That could have led to a confusion, yeah. But that's okay. I'm reasonably okay with things changing around a little bit, but this is just the beginning of the semester, and this goes into 2 semesters. So in the beginning, at least, I'll try to be strict so that we get into this habit of doing it at the right time. But this one, I agree, is my fault. But in general, at least for some time, let's try to stick to it. Later on, I noticed that everyone gets busy, and there is a reason for changing it because it's a small class. I'm okay with it. But for now, let's keep it rigid as much as possible. reasonable?
Yeah.
So are we all of us? 1, 2, 3. Oh, where am I? Where is the? Oh yeah, because it's a classroom. I'm counting you as one person, and where is the whiteboard? I'm thinking. Yeah. Okay, makes sense. Okay. Okay, 4 plus 1, 5. So we're missing someone. Aliyah, I suppose, correct? Yeah. Okay. So homework 1 is due. Now it's 27, right? Thursday. And I posted homework 2. This is September 1, which is a Tuesday. And probably will be one more homework in between. And midterm 1. On the first day. So this is in class. It's not obvious these days. And the rest of it, I think there was a confusion again on how to submit homeworks. Let's be consistent. It always on D2L. And if you're not able to do it, don't contact me. Find a way, I think, because I don't think I'll be the right person. Contact others, your peers, right? They obviously are posting it. At least most of you are in detail, so I'll find out. Apparently, Cam Scanner is the. How do you guys post your homework? Yeah.
Yeah, there's a scanner app on your phone that converts the document, like a picture, to a PDF, and then you just save.
And then does it go to your email, or does it save on your phone itself?
It saves on your phone, but from the app you can choose to share that. And I just share it to the documents on my phone, and then when you click on, upload, you can choose.
I see. So you can
my
save it.
computer, or you can choose.
Okay. You can
Email.
save it in the document.
There's a lot of options it gives you. You can also send it to like one of your online choices like Google or.
That's correct. Yes, someone asked me this yesterday, so that's why I asked.
Yeah. There's a app called Simple Scanner, and there's an app called Cam Scanner. There's a bunch of different ones, but they all work pretty good.
The two things I was suggested is Cam Scanner and Office Lens. Is that also an app? Office Lens, anyone who uses here? I have never used it. Okay. Because I teach a bigger class, which is 50 plus students. For them, it helps to give some directions. Any kind of directions helps.
It works out pretty nice too, because if for instance, if you write down your extra credit problem on your piece of however you write it down, you can fill it out within your notes, and then just take a picture of that section itself. You don't have to like bring out another paper, and so you can just look in your notes and then write your little explanation. Or it's kind of nice.
Okay. Okay. Any other comments or suggestions? Any thoughts? Okay, so I want to today do what we basically a vector space, very basic ideas in there, and in general, this is called curvilinear coordinates. and how do we define vector? And
Can you raise the camera just a little bit, or just zoom out just slightly?
zoom out is not possible apparently. Okay. So the idea is let's work in 2 dimensions for a moment. Let's say, or at least for the ideas, let's keep the 2 dimensions, and the third one could be just the z-axis extended. So we are in 3 dimensions, but all the illustrations are being done in a plane. So if you want to coordinatize your space, you need 2 surfaces. So this could be a surface, and that could be another set of surfaces, right? And this increases, let's call this U1 is equal to, so this is U1, and this could be U2. And each of this curve represents, so U1 is equal to a constant, is a curve in 2 dimensions, but again, if you were in 3 dimensions, that's a surface in 3 dimensions. And similarly, U2 is equal to constant. That's another surface. And intersection of these 2 surfaces usually give you a point in 2 dimensions. In 3 dimensions, you will need 3 such surfaces. So U3 is equal to a constant. Right. So that represents a point in space. A very classic simple example is if these lines are straight, that's your rectangular coordinate system. So this is x is equal to a constant, and that's here. And let's call this x1, and that's x2, which is basically y. So that's so x1 is equal to constant, x2 is equal to constant. It is a way of describing a point in space. A point with respect to some origin, so this is a point. Right. That's your vector R, let's say. So this is with respect to some origin. There is a position vector R. And let's say, let me go one more of it. And I can change this R a little bit to the next point. So that's your R plus dr. So I changed it a little bit. So this is R plus dr. And that leads to a definition for dr. So this is dr. So there is a position, one coordinate, change it a little bit, infinitely, slightly, and that arbitrary movement of the position vector will be dr. And again, there is a similar construction in also. And this can be thought of as if I use partial idea of partial derivatives, this is the same as dui times partial derivative of dui. So let me write this as 1 plus du2 change in the vector with respect to u2 plus change in the vector with respect to u3. Like this is the idea of partial derivative. A total change in a quantity is equal to the sum of the changes in the individual variables. So here we are saying that it depends on 3 variables, u1, u2, and u3. So there is a pattern here, 1, 2, 3. So that tells me that I can write this as a sum, but then I also use the summation convention. If I is repeated, I don't have to write the, I can ignore the sum. It's understood implicitly that there is a sum on I, or sum on I. Right? So that's it. Straight. Okay. Again, irrespective of which coordinate system it is, a small change in the position can be written in terms of partial derivatives with respect to the coordinates. If you want, if I call u1, u2, and u3 as coordinates in this form. Let me call this something special out. Before that, I should say, notice that according to our convention here, I've used a mixed notation. That is a vector, and there are index here. So one should be careful about what this is. On the left-hand side, it is just simply a vector, which I can write it as an index also. On the right-hand side, there is a vector and an index. So in principle, this boxed structure is actually a tensor, right? Because there is a vector and there is another index there. So 2 quantities. So it's basically a tensor. I'll think of it as a matrix multiplying this. For example, if I were to write it in terms of indices, I don't need the vector there. So this is J is equal to dui times drj over dui. Right, so in that sense, the second term there is a tensor of rank 2. But I'm purposefully writing it in a mixed notation. So in the boxed quantity, which is a tensor of rank 2, is being partially written using a vector sign and partially being written using an index, just for visual purposes. Let me define something. So let me define so-called basis vectors. So this will be called basis vector. And this is important that it is as a subscript, not there are 2 choices. I can keep the I if you want downstairs or upstairs, or subscript or superscript. I've chosen this to be a subscript, and this will be defined to be whatever is in the boxed area there. So this is DUI.
So doesn't you said you've just chosen that, but doesn't that change if it's covariant or contravariant?
Yes,
like, it matters, right?
So if you want, this is a covariant basis vector. So this is a covariant basis vector. Almost immediately, I'll define what is a contravariant basis vector, which will be the superscript of a similar quantity. But a line element in terms of these unit vectors is DUI times vector EI. Which is basically a short form of writing EU1 E1 plus EU2 E2 plus EU3 3. And U1, U2, U3 could be any arbitrary arbitrary coordinates. Okay, so that's going to be our definition. Of course, rectangular coordinates are very special out of all such classes. So we can also write so the same vector. So dr does not. So this is a geometrical object. This does not depend on which basis you're choosing. So I can write this as d. If I were in rectangular coordinates, this is dxi times, since rectangular unit vectors are very special, so let me call them xi. So this means ijk. X1, x2, x3 are I, j, and k. So this is dx1 in the x1 direction. It will come out that this is a unit vector, even though it is, I've shown this as, I not described it as a unit vector. It's 2 at alpha plus dx3. It's also equal to I times EI, which is du1 on some basis vector, not necessarily a unit vector, plus du2 plus du3. 3. Okay. So that's sort of our definition. And then the question comes, if we know U1, U2, and U3, what is our, what are these unit vectors? So let's do an example just to describe what's going on. So let's do an example. And the example is a cylindrical coordinate. Cylindrical coordinates. The examples that we will do, I will do here, will be for orthogonal coordinates. Usually cylindrical, spherical, and rectangular is what we will do. But these constructions are true for any coordinate system, and there's very simple coordinate system which is not orthogonal but actually planar is what is done in your homework. So which is useful in crystallography. You might have heard of reciprocal basis in crystallography. So if you're not, what basically it is that if you think of a metallic crystal, how do you see it using an experiment? You will actually shine it with an X-ray and look for the X-ray pattern. Right? You might have seen popular description of this. And the pattern that you see is actually the reciprocal basis of what the crystal basis is. So if you want to describe a crystal in the geometric sense, you would use the covariant basis. But the X-ray image that you see actually is the contravariant basis. So you're not actually seeing the crystal itself, you're seeing it in another space, if you want, which is called the reciprocal space. And that is explored in your homework. So I take a very simple example, and you actually do exactly what we are doing in the class. For cylindrical coordinates, you do that for a lattice structure there. So hopefully it will give some insight into what's going on. So cylindrical coordinates, remember the way we have described this, we want to begin with some surfaces, right? We have to have some intersection of surfaces. Here it is x, y, x equal to constant, y is equal to constant. And here this is some arbitrary two family of surfaces. And cylindrical coordinates, these are circles of different radii. And you also have half lines. The half line means you start from the origin and go all the way to infinity. That's another family of lines. And the intersection of this is what describes cylindrical coordinates, and of course z is equal to constant is also there. So what are the variables? You would say rho, which is equal to x squared plus y squared. That's your u1, let's say. This is your u1. Whatever I said, described there. So that's my u1. u2 is, so this will be circles, right? So this will be u rho is equal to constant. That's a surface. The other one is the angle phi that we use in cylindrical coordinates, or the polar angle. Phi is tan inverse of y over x. And this will be your u2. The second surface, which is described by this line here. So that's phi is equal to a constant. I try to visualize those surfaces, and of course there is a third one, right? It is just z, and z is just equal to z on both. So that is x, y, z, and z remains z even in the third, even in the transform coordinates. So it's u3. So that's your u1, u2, and u3, and I used x1 is equal to x, x2 is equal to y, and x3 is equal to z. So that's another, that's your rectangular coordinates. Okay. So what is my E1? So E1, so according to this description, my line element, maybe I should define that also, right? So this is this would be called a line element. So it's a small line element in your space. dr is equal to ui times ei in terms of the unit vectors, covariant basis vectors, not unit vectors actually. Unit vectors will be when you divide it by its magnitude. So ei is, or let's start with E1. Right? So let's do E1. E1 is dr over du1, 1 in the super. Notice what is happening here. 1 on the left hand side is in the subscript, but 1 on the right hand side is in the super script. Typically how it works is that when you, any subscript or superscript in the numerator, when you take it to the denominator, it swaps its position. If index was on the superscript in the numerator, when it goes to the denominator, it changes sign. So that's what happens all the time. It is not that I actually forced it. The way I defined it, that is a pattern that you will see all the time. The way I have constructed. So what is this equal to? So this is the same as u1 for us is d by d rho. And we want to find this out. So let's write our position vector in terms of, first let's begin by writing this as xi. Where I hat here is x1. So this is, so temporarily let's call this I hat. This is j hat, and that's k hat. It's not necessary, but I think it's useful to, otherwise there are too many variables. So that's xi hat plus yj hat plus k hat times z. In the description here, I wrote rho, phi, and z in terms of the rectangular coordinates. I can do the opposite also, right? So this is rho cosine phi. This is rho sine phi. And z is z itself. So either way is, that comes from the geometry, from which coordinates, which surfaces are we talking about. Since I want to take the partial derivative of x with respect to rho, I would like to write x in terms of rho and phi. So let me explicitly do that. So this is d by d rho of rho cosine phi I hat direction plus rho sine phi. Okay. Hat direction plus z in the k hat direction. Take the derivative with rho. This gives you, since it's partial derivatives, I don't worry about angle phi. It's only the rho's that matters. So this is cosine of phi in the I hat direction plus sine phi in the j hat direction plus 0 in the k. Which we know is the unit vector, which is rho hat. Right? So let's give it a, what's the magnitude of that vector? Is it a unit vector or is it not a unit vector? Right, it is a unit vector because cosine square phi plus sine square phi is 1. So it is a unit vector. Again, like we used ijk, let's use familiar unit vectors in our head. So this is also rho hat, right? This is just a symbol at this point. Right? So what we are realizing is that E1, even though I didn't say it was a unit vector, it came out to be a unit vector. It's not necessary that it will always come out to be a unit vector in this construction. Here, it turned out to be a unit vector. Okay. Any questions at this stage?
Could you zoom in the camera a little bit so that we can see the right corner? Thank you.
Did you want it zoomed in or just moved?
That's fine. That's
good enough. Yeah. Okay. So let me try to squeeze in the second unit vector E2 right here itself before I move to the other boat. The E2 will be dr by du2, which is dr by d phi. So that's a second vector. And I'm not explicitly going to write it, so r is right here, right? That's your r. I have to take the derivative of this with respect to phi. And if I take the derivative with respect to phi this time, cosine becomes sine with a negative sign, and sine becomes a cosine, and rho stays. So this is minus rho sine phi in the I direction plus rho cosine phi in the j direction. Is that a unit vector? Is that a unit vector? And what's the magnitude of that vector? Rho, right? Rho, yeah. So yeah, so when you square this, that's rho squared, but then magnitude is square root of that. So it's rho, so it's not a unit vector. So, but we do know that phi hat looks, so this is nothing but rho times phi hat, if you recall from your definition of rho and phi. So let me quickly remind you what rho and phi is. Let's change. Can I move the camera, by the way? I think I did. Are you guys good with? Right. Okay. So let's draw this rho and phi. So typically, if you have a circle, that's your point here. That's rho hat, and that's your phi hat. Okay. If you move this to the at the origin, that's your rho hat, which makes an angle phi. It's clear from the geometry if this was unit, this was of length 1, and using the right triangle geometry, we know that it is cosine phi and sine phi. Where is phi hat? Phi hat is perpendicular to rho hat, so that's here. And it is of the same length, so that's unit length. If this is angle phi, this is 90 minus phi, and that's angle phi. And again, now this is in the second quadrant, so that tells you that the x component, which is actually opposite to the angle, that's a sine phi, and the y coordinate is cosine phi. And so using that geometry, this is how we define rho hat. So that's rho hat is sine phi, j hat, and phi hat is minus sine phi in the I direction plus cosine phi in the j direction. These are, if you want definitions, these are really not dependent on what I'm defining as basis vectors. And what I've learned from here is that by doing this, or defining this line element, is that the line element is ui times ei, where E1 is your rho hat.
Slightly to the left.
Slightly to the left.
Perfect. Thank you.
Okay. So E1 is actually, it turns out to be a rho hat itself. E2 turns out to be rho times phi hat. Correct? And E3, if we do this, so what will be E3? Can you guys quickly calculate E3?
Should be K.
K, yes. Z hat or K, right? Yeah, exactly. So it's K hat. So it's a unit vector. Good. These are not unit vectors, as we see, especially the second one. Sometimes some of them are. So it's good to define a unit vector. So let's, let me define what are called scale factors. So these will be scale factors. Right, of a coordinate system, and that will be the magnitude of this vectors. E1 magnitude, I'll define it to be H1. Sometimes I will also write this as H rho, but this, or let us say also H rho. Like H1 is sufficient, but since we are in cylindrical, it is H rho. But H1 is magnitude of rho hat is just 1.
Let's just, oh, okay, never mind.
E2 magnitude of H2, that's exactly rho. And E3 is H3, that's 1. Notice, in this sense, even the dimensions are not the same, right? H1, H2, H3 doesn't have to have the same dimension. Like the basis vectors do not have the same dimension. So be careful about that. It is like saying that the angle, right? The coordinates are phi and rho. They don't have the same dimensions. Phi is an angle, rho is a distance. It is not having the same dimensions. Okay, so that's your covariant basis vectors, and this is like saying if you have. Let me go back to this diagram here. If we are in here, this is like saying you go along a line, right? So for example, if you're doing ray optics, think of a ray versus what's the other wavefront? What's the connection between a ray and a wavefront?
The ray is the direction of the propagation, right?
Uh-huh.
I'm thinking of like Huygens sources.
Yes, exactly that. Yeah. If you realize, or all of you are aware of what is a wavefront and a ray, right? At least terminology-wise in optics. Yes, no? Tell me no? No. No. Okay. So let's change. So let's think of a source of light. This is a light source, and if it was spherical waves, this is how light as a wave moves around. Is that a familiar idea? So think of this as a source of light.
Basically like dropping a rock in some water.
Yes, it's exactly like dropping a rock in the water. It creates a disturbance. That disturbance moves outward. And the propagation of that happens in a straight line in each direction. Or doesn't have to be a straight line, at least in this circular sense, this is a straight line. So this is called a direction of propagation, locally, direction of propagation. And that's a ray. So that's a ray. But as a wave, this is so this is a wave front, which is a surface perpendicular to array. That means to say that if you have a family of surfaces, those surfaces are equally described by unit vectors that are perpendicular to it. Either you can say that I want to work with surfaces, or I say that I'm interested in the unit vectors that describe a surface at every point of the surface. So there are two ways of describing. So either give me surfaces or surface, let's say. So this is surface is the analog of a wavefront. But a surface is uniquely described by what is called normal vectors, which is the idea of array. So a surface and a normal vector is connected in the same way as wavefront and array is connected. So that's the physical connection. If you're not familiar with the idea of array and wavefront, that doesn't help much.
Does the double arrow mean analogous? Is that what that actually means?
No, analogous usually has to, so usually in mathematics at least, analogous means 3 lines, I think. That's what you use. Equivalent maybe. That means the equivalent. Here I just mean a surface suggests wavefronts. It's very descriptive, nothing precise in that. Right? So what I mean is a surface is like a wavefront. That's all I mean. Very qualitatively what that suggests. So nothing deep in there. Helps? Does that answer your question, Jordan? Yeah, okay. Okay. So with that idea in mind, here we are talking about line elements. It should be possible to describe the coordinates in terms of normal vectors. So these are rays, if you want, line elements. That is a similar description in terms of normal vectors. So let me define this as contravariant basis vectors, which are basically normal vectors. And often in many coordinate systems, these two are the same. Right? There is no difference between the contravariant and covariant. A classic example is a rectangular coordinate system, and many of the standard coordinate system, they are the same. In your homework, you will do an exercise where these two will not be the same. So I'll suggest that you guys try to have a visual picture of that, and a classic example is the crystallography, where a crystal and the reciprocal basis. So try to get a feel for what they are. Very useful. It's very used in all contexts. Like quantum mechanics also has the same thing. You have one space and you go to the dual space, right? In quantum mechanics, you call it the dual space. So it's useful, but this is a very simplistic version. Can be extended however you want. General relativity is also done in the same manner. These are very basic rudiments of. Okay, so how do we define contravariant vectors? Instead of saying these are line elements, we want to define it as normal vectors. So there, how you would say it is, the way you would define it is that any change in the coordinates u, du, I can be written as, let me just define it in this. Yeah, let me just define my unit vectors as E, again E itself, but this time not subscript, superscript. A very small change, contravariant unit vector will be defined to be the gradient of each of the surfaces. That's it. Okay. Remember that gradient of any variable means should be interpreted as gradient of that variable being a constant. That's a family of normal vectors and or normal vectors to that surface.
So I have a quick question too. So like on the electromagnetics homework, when I've just always done gradients without doing the arrow over the top, does it exactly matter?
Here, this vector.
Yeah, is it if you just leave it out and write the?
Yeah. Now, this is it's a notation. So now what happens is that in typography you use boldface, right? So this is what a gradient is. If I'm typing in my homework, for example, there is no vector sign on top, but the idea is that it's a boldface.
I'm saying in general, like if I didn't include the arrow over the.
It will be confusing. It will be confusing.
Okay.
You know that it's a vector.
By looking at it?
Just by looking at it. For example, let's say I have, what's the difference between A and vector A? So this is a vector that's a magnitude, correct?
Mm-hmm.
So if I don't write that arrow, how do I know the difference between the two?
Yeah, I get that. I guess I've just never added the arrow over the gradient sign.
Yeah, so at least I'm usually picky, so I keep pushing in my grading that put an arrow. I don't take off points if it's a complicated homework, but if it's put it like this, if it is an undergraduate work, then I'm usually picky about it. I sometimes even take off. It's like units. If you don't put in the units of a quantity, how important is it? Yes, it is important, but then if you're talking about a complicated concept, then you ignore the units often.
Yeah.
So something like that. So does that answer your question?
Yeah, I mean, it answered my question, I guess. I guess when I see the gradient, I'm just assuming that it's the vector, you know.
Yeah,
not adding that, but
it's a good habit to keep a vector sign.
okay.
But again, style comes in.
I'll just add it before I upload.
Excuse me, doctor. I used to put a bar only, no arrow. Is that okay?
Yeah, that's okay again. But then again, there will be situations where sometimes in physics, a bar has a meaning, right? Sometimes it is complex transpose, or there are various meanings to that. And then you have to differentiate between them. Again, it is contextual. If it is obvious that this is a vector, that's okay. But it's like my R and gamma, right? So I write R and gamma, so that's a classic example. I suppose as far as both don't come together, it is okay. As far as you put it in a corner of your page that this is what I mean, then it's okay, I suppose. It should be unambiguous, that's all. I think, does that help? Yeah. So, yeah.
Excuse me, could we think about the covariant basis vectors and the contravariant basis vectors as symmetrical at any sense?
Symmetrical in what sense? What do you mean by symmetry? Which symmetry?
Oh, I mean, covariant and contravariant, is that kind of symmetry we're talking about, or kind of opposite?
Yes.
Reciprocals or something.
They are, yes. So that's where when you do the homework, you will see this very clearly. It turns out that orthogonal coordinate systems have a lot of simplicity in that, so this doesn't bring out that very well. But I construct an example in your homework. So basically, this is what your homework has. So this is one of the space, and the other one is not orthogonal. This is also a perfect coordinate system, right? Give me any point, I can specify that very uniquely using two lines. Like they don't have to be perpendicular. And now for this, we can actually, so this is x is equal to constant, right? That's the point. But y now is y is equal to mx plus c, right? So there's a slope that comes in, and c is a variable here, right? So so this is the intersect here. So this is c. As I increase my c, my lines keep going, so it's not y on the side. So x and c are good coordinates. Give me my x, that specifies which vertical line I am on, and give me my c, it specifies which inclined line I am on, and the intersection of the two is a good coordinate system. And then again, you can define what are the unit vectors associated, what is the basis vector associated with this c, what is the contravariant, what is the covariant, and they won't be the same, right? Unlike cylindrical coordinates, rectangular coordinates, they all contravariant and covariant come out to be the same. So it's not very illustrative of what these vectors mean. In this case, they will come out to be different, and they're actually called reciprocal bases. And remember, crystal, if you're thinking of a crystal, symmetries in a crystal, they're exactly like this, right? They need not be perpendicular. And then when an X-ray sees that, X-ray will not see this symmetry, it will see the reciprocal symmetry. So beautiful connection there. But yeah, do the example and you should see it. So that's my answer to your question. Is there a symmetry? Yes, there is. It's called the reciprocal symmetry. But I'll let you explore that in the homework. Okay. So. Any other comments, questions? Okay, so that's contravariant basis vector. So let's, and this is clear what this means, right? This is the actual gradient operator. So we are actually evaluating this for the cylindrical coordinates. So example again, right? So specific example for cylindrical coordinates. So let's calculate E1, E2, and E3, right? So that's gradient of this is rho. So this is I hat times d rho over dx plus j hat. So let me write the rho hat separately. So this is d by dy plus k hat d by dz. Acting on rho, since I want the variation in rho with respect to x, y, z, I need the dependence of rho in x, y, and z. So I write that as x squared plus y squared. And that's equal to I hat times x over x squared plus y squared. The square root makes it go to the denominator, and then you have to take the derivative of the argument of the square root. So that's 2 times x, the factor of 2 cancels out. And this is j hat y over x squared plus y squared plus 0. And if you use the geometry of the cylindrical coordinate, it turns out that this is exactly cosine phi, and that's exactly sine phi. And this again comes out to be rho hat again. So that's why this is not a great example, because they are the same, right? One came out to be rho hat there, came out to be same. So whatever Khaled was asking, it doesn't come out very cleanly. Why do we need these two coordinate systems? And that's where the homework plays in. But rho hat, now do the same thing for E2. So let's do E2. that's gradient of the angle phi, right? That's the second variable, so u2. Let me write that as u2 first. It's u2, so that's gradient of the angle phi, which is I hat by dx plus k hat d by dy plus k hat by dz of phi, which is, I want to write it in terms of x and y, so that's tan inverse of y over x.
So is that just the vector phi is equal to E2?
Vector phi.
Phi is equal to E2, which is the gradient of phi? I'm confused a little bit.
Ask me again, I'm not sure what you mean. You mean this one?
Yeah, E2, is that
Oh.
just equal to phi?
No, no, I don't think so. Let me see. Can you guys see this better? Yeah. So E2 is this, right? Gradient of U2. Remember your, okay, let's go back to 1.
Okay, I got it. We're good. I got it.
So here I defined this rho as U1, phi as U2, and Z as U3.
Yeah, I got
So
you now.
E1, E2, E3 is the gradient of these three. Gradient means the normal vectors associated with those surfaces. Phi is equal to constant, rho is equal to. So we are talking about the unit vector that's perpendicular to these lines. Again, visually we know that that's going to be coming out to be phi. This has to be changed a little. Okay. What is d by dx of tan inverse of y over x? So usually what I, at least various, if you know the differentiation of tan inverse, you can immediately do it. I usually don't remember it, so I say this is tan inverse of y over x. So tangent phi is y over x. Probably there are easier ways of doing this. So this is secant square phi d phi, this is partial phi with respect to, let's say, x, right, is equal to minus y over x squared. Right. That's all. So take a derivative on this side plus that side. Actually, best is if you want to write this as d phi, and this is dx, and then this is plus dy over x. That's partial derivative also is captured. And here, keep y is equal to constant. What is d phi over dx? So that's minus y over x squared divided by secant square of phi, which is minus y cosine square phi, and this is all like this. Minus y is rho sine phi, right? And x is rho cosine square phi, rho square cosine square phi. So cosine square cancels out. So this is minus sine phi over rho. So it's in the denominator. Same thing if you do it with d phi by dy. This will come out to be cosine phi over rho. So what we have here is that E2 is equal to I times a hat times cosine phi. No, and sine phi. So minus sine phi over rho in the I hat direction plus cosine phi over rho in the j hat direction plus 0 times k. Like earlier, this is not a unit vector. Right? So this is actually phi hat again. but this time rho is in the denominator. And E3 is the easier one. That just comes out of the k hat again. So if I were to summarize what we have as of now, so for at least for cylindrical coordinates, we have E1.
Can you move the board? Section? Or not the board, but the camera.
So E1 came out to be a rho hat. E2 came out to be rho times phi hat. And E3 came out to be k hat, or z hat. And this is covariant basis vectors and contravariant basis vectors comes out to be E1 on superscript. That again came out to be rho hat. E2 came out to be phi hat over rho, and E3 is k hat. That is something one can, so let's construct a, so there is 3 of them here, 3 of them there, and I can figure out, let me take a dot product of either one of this. So let me do I, so I could be, so I is a contravariant dotted with J, and I could be 1, 2, or 3, and J could be 1, 2, or 3, and dot product. So this is to say this dotted with this dotted with this dotted with this. So there are 9 of them. So all 9 of them, I arrange them like this. So this is equal to E. This is like a mid. So after I take the dot product with the numbers, so this is E1 dotted with E1. E1 dotted with E2, E1 dotted with E3. And I want to evaluate each one of them. 2 dotted with E1, 3, 1. That's a matrix here. That's a way of arranging them. What is E1 dotted with E1? E1 dotted with, so this one dotted with this one, rho hat dotted with rho hat, that comes out to be 1. E1 dotted with E2, rho hat dotted with phi hat, that's 0, right? They're perpendicular to each other, that's 0. E1 dotted with E3, that's also 0. This is 0. E2 dotted with E2, notice there is a 1 over rho here, there is a rho here. They were not unit vectors, but somehow its magnitude came out to be exactly inverse of each other, and it's again 1. Right? That was And you'll see that that's not really a coincidence, it will be in general. So this is 0, this is 0, 0, 1. So this is actually delta I j. So dot with Ej, so the summary is that this is delta Ij. So by construction, these are orthogonal. These are orthogonal in this sense. Notice these are not the normal orthogonality, right? Normal orthogonality, you would say, take the vector and multiply with that itself. Here we're taking one from the covariant space, the other from the contravariant space, and that's orthogonal. So this is orthogonality. Of the basis vectors. Why does this happen? If one would be curious, is this always true? Is this true for any coordinate system, or is it just because it was cylindrical coordinate system? So let's go back to our definition here. What was EI? So this was partial derivative of R, like the vector R, with respect to DUI, right? And the gradient is this is equal if you want, so right? This is equal to dotted with gradient of U. This time, since it's J, so that's J. So that's what it is. But what is that equal to? X.
Are they?
Yeah.
Are those? I thought E lower j was dr.
Oh, yeah, you're right. Sorry for that. So I think this is yes, that's correct. Did I write this correct? Yeah. So you want to write this the other way, right? This was the gradient, correct? Thank you. So this is gradient of U of I jotted with, thank you. So this is E of j is d of r of du of j. And this time I wrote it correctly, hopefully. Okay, so that's equal to, if I explicitly write this, this is dui over, I can write this as d of r, right? So as the gradient operator can be thought of as, this means the gradient operator, x, y, and with respect to x, with respect to y, with respect to z. Dotted with d of r over d of j. And since this has this x dx, dy dz, and this actually cancels out. Like if you think of this as an expansion, that comes out much better. So this actually, like, argue why that cancels out, like try to interpret that. So that's basically partial, the statement of partial derivative. Right? dr written in that sense is nothing but partial derivative. Or let me write that explicitly. So this is dui dx, dx, duj plus dui, dy, y over dj plus di, z, dz over dj. And that's a chain rule if you want, so that that's goes away, and you have dui with respect to duj. Right? So this is like saying a derivative of x with respect to y. Like inside a set of coordinates, they are considered to be independent of each other. And here it is very clear that this is delta. So irrespective of which coordinate system you're working with, as far as you have a unique way of coordinatizing a space with a family of surfaces, this construction guarantees you orthogonal basis vectors. Okay, so we have defined two sets of basis vectors, covariant and contravariant, and by construction they're always orthogonal. And now in the next step, in the next class, we will actually define what is a metric associated with it, and we will define completeness relation, right? In the E&M class, we have introduced what is this. This comes out to be always equal to 1, right? That's inbuilt in these constructions there. And from there, one can build a so-called curvature tensor, the derivative of these unit vectors and so on. But we will limit ourselves to only a little bit. We won't go too far.
Yeah.
Stick to the basic ideas. Okay, so did I give you an extra credit problem? Let's see. I did not, right? Yeah, so oh yes, spherical coordinates, right? What is if in spherical coordinates, which are determined by r, theta, and phi, right? So this is u1, this is u2, and this is u3. So find the scale factors over that. Find the scale factors in spherical coordinates, right? So basically find the unit vectors, the covariant unit vectors, not the contravariant unit vectors, and then find the magnitude of those unit vectors. That's what is called the scale factor. Remember that if you had done the scale factor for the contravariant, they will come out to be usually the inverse of those that we found in this. Yeah, that's all. Any comments, questions?
So we have to find the scale factors in the spherical coordinates?
Yes, exactly. Is that clear? So for what you would do for that is find your 3 I, right? So this is d r over d u I, right? Do this for r, theta, and phi, and then find the magnitude of them. And interpret this. What does it mean? Interpret the scale factors there. The length, I think we already did an extra credit where you figure out that there is a volume element in a spherical coordinate and the length of those is r d theta or n theta d theta. They are the same. Scale factors are exactly that. So scale factors sort of capture the line elements in each directions, or how much you have to scale them. I think that's the point. Okay, does that help? Okay. Thank you. So is it okay if I keep the second homework due on Tuesday, even though the first is on Thursday? So it's a short while between the homeworks, but I think hopefully, I think the first homework is relatively, actually that's related to what we have here. There you find the unit vector. So overall it connects well. Okay, thank you.
Thank you.
Thank you.
Bye.
Much.
Thank you.
this